So we heard ARM TechCon. So who are you?
I'm Brian Jeff. I'm a product line manager with ARM. I look after big.LITTLE as the technology and about half of the Cortex-A CPUs in our product family.
So, product manager, what is that?
So it's a marketing function, but so I'm also looking at the definition of our roadmap and the next products that we're designing, and I engage with the silicon partners that use ARM technology to build the chips that are making our lives better, mobile phones, things like that.
So you had a presentation, a session, and there was lots of people, it's packed,
yes.
And basically you explained big.LITTLE, or?
Sure, yeah, so I think the session was packed because there's quite a lot of interest in big.LITTLE. It's a technology where we combine our high performance cores with very high efficiency cores, and we combine them in a way that they look like one thing to the software. So they're cache coherent, the software can map work to the big cores or the little cores. And what we find is that most of the time, your mobile phone, these small cores are good enough. And if you can run on those good enough cores, you save enormous amounts of energy. And it also reserves energy for the time when you really want to burst to peak levels of performance on the big cores, or maybe allocate more capacity to the graphics processor to improve the user experience that way. So we're seeing really good results from big.LITTLE, and fundamentally it's that pairing of the big core and the little core in this tight way that looks like one thing to the software, like one processor.
So what's been the reception from the industry?
Yeah, so the reception has been very strong. I think we're just now starting to see silicon in production. We've got several designs in production with our various partners. I think there's nearly a dozen designs that are about to go through with big.LITTLE on board. So the reception has been very strong. It's just coming into the market. So this has been something that's really a long time coming. Personally, I've presented big.LITTLE at the last 3 TechCons. Last year we presented it and we showed it on our test chip. The year before that, we really showed it on software models, and it was more of a concept technology. But that's been how long the incubation has been. And now we're actually seeing it on production silicon devices from multiple partners, and it's in shipping devices today, and the newest versions of the software I think are going to make their way into devices next year.
So what kind of questions were people asking? There was a Q&A for like 20 minutes?
Sure, yeah.
What did people ask you?
They asked a lot of different questions. Some were about the architecture itself. Why did we organize the cores behind separate L2 caches? How does the coherence work? So there were questions about the architecture itself from a hardware IP standpoint. A number of the questions actually were about the software. So in the global task scheduling model, in that mode you can actually turn on all of the cores at one time. So if you have a 4+4 system with 4 big and 4 little cores, that model of the software, you can turn all the cores on at once, or you can use as many of them as needed simultaneously. And I think in the earlier versions of the software, a lot of people came to understand big.LITTLE based on the mode where you switched and used one or the other. So I think that was a source of questions for us, is how can the software enable the cores, the big cores and the little cores to be awake at the same time and still cooperating with the OS and dealing with the threads that need to run.
So does that mean, let's say an Android phone that's on IKS could just get a new software update and be an HMP? Or is that
that's up to the hardware manufacturers, but from the technology standpoint, any hardware that is built to support IKS could also run MP. It's really just a software difference. If you have that cache coherency between the big and little cluster, you can run either mode. And we think the software has matured to the point now that there's no reason not to do the newer mode, the full HMP mode.
So mature, that means it has taken time to be stable, or?
Yeah, we've been testing it. The code has actually been stable since earlier this year. So a lot of what we've been doing is tuning the performance of the system and some of the parameters of big.LITTLE, things like up and down migration thresholds and DVFS parameters to make it work well in the system. So I think there's been a maturation along that dimension. We've also been working to upstream the code, so that process has been something kind of long in coming, and we're not in the upstream with all the components yet, but we do have a stable kernel version that partners can take and use that to go to production. And so that's what we see some of our partners doing now, is going to production with the LSK, the Linaro stable kernel release, and using that as the basis. And Android just sits on top of that. So it's a modified kernel scheduler inside Linux. Android sits on top of that, and all of our benchmarks and demos were based on Android running on top of that kind of stack.
So it's all about Linux.
Primarily, yeah. The changes that we made to big.LITTLE are in the Linux kernel, and in some of the versions we modified the device, the DVFS driver, but primarily we modified the kernel scheduler and added some things to that to enable big.LITTLE to work. So it really is in Linux today.
So
it can go elsewhere, but that's where it is now.
Is there a lot of magic in there, or is it like really advanced, like kind of guessing which core is best, or kind of like figuring it out automatically somehow without like the application telling it specifically what to do?
So it is quite advanced in how that is done. The software that deals with the decision of whether to run on a big core or little core is in the kernel scheduler, and that software is looking thread by thread at the load history of that thread and deciding, hey, this thread required a lot of performance last few times it ran, or it required little. So we have a good guess at the beginning because we keep track of each thread. And while the threads are running, we dynamically adjust. So if something's been sitting in the run queue too long, we can do an up migration and move it to a big core. And we keep track of that migration later on so that the next time we can guess better. So that's how the software works. It is complex, but what I'll say is that the complexity is really in kernel space, and for an OEM or a silicon partner, what they'll need to do is just take that patch and use it, and for them the complexity is kind of hidden under the hood, just in the way that the standard Linux scheduler handles things today, for example in the standard SMP kernel.
Can it get better and better and just get upgrades and get a better HMP, and that's the point? Sure,
it can improve. I think the basic infrastructure is in place. Some improvements we might expect is, for example, the use of affinity. So you can say, hey, this thread or that thread is a low performance thread, so let's always run it on an A7 class of core. And conversely, you could identify through affinity threads that are high performance so that they're known a priori, and you don't have to do this checking or load history. So that is an area where you could probably improve things. There's additional tuning that could come in. And another question that actually came up during the event was about virtualization. So today in phones, there's not really a VM in place. You use a single OS, but there is this interest in bring your own device, maybe having an enterprise OS and a consumer OS on the same device and managed differently. And so that would require a hypervisor or a virtual machine. And so there's potential improvements in big.LITTLE to allow it to interoperate with a VM and kind of work together in that environment.
So do you, what's called, I mean, this is a long-term architecture that's, for example, in the 64-bit is 53, 57.
Sure.
So why, I mean, can you try to explain why there's a need for small cores and big cores? Is it just because there's enough space on the die, because if the nanometers are getting so small and you need to fill it up with something, or is it absolutely necessary? You can't, for example, have a big core do small stuff automatically?
Sure. So the cores look identical to software. So architecturally, they're identical. They run all the same instructions. And so anything you could run on a big core, you could run on a little core, and vice versa. The difference is in performance. So the little cores, it tend to be about half the performance level of the big cores, but their energy efficiency is about 3 times that of the big core. So anytime you can get away with running something in a little core, you're better off to do so. You'll save quite a bit of energy. And that can be used to improve battery life. It can be used to allocate more power to other parts of the system, like the graphics processor. It can be used to handle kind of a bursting mode where you need to, render a web page. And right after when you render a web page, you want to run things very, very fast. But when you're done, when you're just scrolling down the page or reading the page, there's not much you need to do. So I could remain on the big core the whole time after I render the web page, but I could save a lot of power if I just moved to the little core, and that helps things like battery life. And what we are also seeing with the global task scheduling versions of big.LITTLE, because you can run the big cores and little cores at the same time, there's some added performance for threaded workloads. If you can run all those at the same time, you can get more performance than you could get if just the big cores were in there. And if you just wanted to double the number of big cores, that would really have an impact on die area. So the added area for the little cores is actually quite small. Each one of them is about a half a millimeter squared. So because they're so small, it's not an expensive thing to put them onto the system. And they actually do quite a lot in terms of helping you manage power and deliver performance in these special use cases.
So the idea to do this, big.LITTLE, came because of the technology that arrives with making chips smaller. It's connected?
The idea really, it's been a long time coming. So we've known for a while that mobile workloads are very bursty. You need these peaks of performance, but most of the time you don't need that much. And the kind of processor you would design ideally to deal with those bursts of performance is a quite different processor than the kind you would design for the efficient case, the more common 95% of the time case. So we've known for a while that this disparity or this burstiness existed, and it's just been a long time in coming to be able to develop the architectures to work tightly together in the way that they do now.
All right, so how about the heterogeneous computing? How does that fit with big.LITTLE?
Sure, it fits quite well. So heterogeneous computing is the idea that you can take a graphics processor and use that for some of the work, not just processing images or not just rendering images, but also processing some of the data that's in the images or maybe doing floating point computations. So a GPU is inherently a very parallel architecture that can do a lot of things at once. And there's certain kinds of work you'd want to send over to that. And just like with a big.LITTLE combination, there's some kinds of work that benefit from a high performance CPU. There's some kinds of work that you want to offload to a graphics processor. So they work quite well together. The model for software distributing the work is a little bit different between the big and little processor and the GPU, because the GPU is a different architecture. But they work quite well together, and I think that's something you've seen in the ARM booth with the big plus little plus Mali demos that are there. You've seen this interoperation and this graph of what the code is doing while you're doing these various demos, allocating some work to the big cores, some work to the little cores, and then some to the graphics processor.
So to allocate stuff to the different cores and some to the graphics, does it have to be in the app, like the Android app, or can it just be automatic?
So today,
like you don't even need to think about it if you make apps.
Right. I think the goal is to make it a bit more automatic. Today, there are API calls where you take the work you want to offload to a GPU and send it off using RenderScript or OpenCL calls. So today it's done through an API. I think there's a goal towards making that more automatic. And ARM is a founding member of the HSA, the Heterogeneous Systems Association. We're working together with the community to try to develop the standards to make that happen.
So ARM announced the ARM Cortex A12.
Oh yes,
and that's not big.LITTLE yet.
Mm-hmm.
Why not?
It's coming. It's coming. I think our goal with the A12 was to, enable big.LITTLE just like we have with the rest of the roadmap, but we wanted to deliver it fast. We saw a need in the market to have a processor optimized for the mid-range, and in the mid-range, there's quite a good use case for using just the Cortex A12 processor by itself. It'll be better when big.LITTLE comes along, but we didn't want to delay the A12 for another year or for another 6 months until the big.LITTLE was there. We wanted to enable it this year so that partners could tape out this year and go to production in the early part of next year with the standalone versions of it, and then come with follow-on products that incorporate A7 and A12 together in a big.LITTLE pairing.
Could I ask something, because I'm wondering? So when Qualcomm does what they do,
right,
which they call, I forgot what they call it, but how would you compare?
Asymmetric multiprocessing?
Yeah.
Right.
So how is their solution compared to big.LITTLE?
Yeah, it's a different approach to try to do the same thing, where you adapt the performance capacity of the CPUs to the workload. And so what they're doing is scaling the voltage of individual cores in the cluster. And it's quite a clever approach. I think it's quite good, and it's an example, the ARM ecosystem is diverse, and different partners are trying different things to optimize for mobile and other markets. So I think it's quite a good approach. We also do DVFS. We do it a little bit differently. So for the ARM cores, the voltage and frequency for the big cluster is the same. It's one voltage and one frequency, and that's scaled dynamically. And on the little cluster, there's another voltage and frequency domain there. And then individual cores can be shut down or woken up as necessary. So for us, we thought big.LITTLE with voltages for each cluster made a lot of sense, because you get the benefit of the big core and then a different microarchitecture for the little core, and you get the voltage difference there. Having a voltage difference in the cluster can also be useful, and we think they're both good approaches. We fundamentally think big.LITTLE is an approach that gives you more degrees of freedom in terms of tuning the performance capacity to the needs of the workload. but we're seeing those solutions compete in the market, and I think both sides are going to evolve over time as we kind of see the strength of each approach.
So just so I can try to understand, you couldn't just take a big core and just put the frequency very low to save power and then go up again and totally automatic, but it's still better to have small cores do the small stuff.
Yeah, you can do that. So you can, and we're obviously doing that right now with our big cores. We've scaled them up and down in voltage and frequency. So yes, we are doing that. You can do better when you have a little core there as well, because you have that same voltage and frequency range for the little cores, and that gives you a much lower point in terms of the leakage power and in terms of dynamic power when you're ramping things down to lower frequencies if you run that on a little core. And also, in the presence of a little core, your physical design for the big processor can be approached differently. If you know that you have a little CPU cluster that's handling all those low intensity tasks, then the big processor can really be optimized for running fast, doing what it does best. And you don't have to worry as much for the leakage of the big processor at the low point, because you only run it at a minimum of maybe 800 or 800 megahertz, 1 gigahertz. So it does give you some different choices and different design freedoms because of the presence of the little.
So in a normal use case, a phone, let's say,
yes,
big little phone, very rarely needs the full performance of every core running at the same time, right? In a normal use case. So most of the time an ARM processor is very low performance, right? Very low power, and that's how that's what's cool about ARM, right? Sorry I ask it like this, but so most of the time, like 99.9% of the time, you're not using Is that
it depends on the workload. So if you're playing something like Angry Birds or making a phone call, I would say it's 100% of the time you're on an A7. What I showed in the talk was that there are workloads where maybe 5% of the time you're on a big processor. There's some where you're on the big processor 20% of the time, really intensive games. But those use cases are fewer. One of the things I'll point to is the number of Cortex A7 based phones that are in the market. So there are a number of these, at 1.2 gigahertz, 1.5 gigahertz. One example is the TCL Idle X running a 1.5 gigahertz MediaTek Cortex A7, 4 cores. And I've used the phone. It is very hard to discern the performance delivered on that device versus some of the other high-end devices I've used and owned. So you're getting very good performance out of the little core by itself when it's the only phone or the only CPU in these low-cost phones. So, I think having just enough performance, having right-size compute, that's something ARM is really good at, and we really focus on not over-engineering things. On big.LITTLE, what it does is it enables high-end systems where you need that peak performance to get that extra boost. And that allows app developers to develop new and innovative things that take advantage of all that capacity. But most of the time, you're right, you only need the A7s in a lot of the use cases, in an everyday situation with your phone or your tablet.
So in a low-cost dual-core Cortex A7 is just 2 half-a-millimeter square Cortex A7s in there.
Yeah,
it's tiny.
Right. There's a bit of L2 and other infrastructure in that, obviously, and then you've got probably baseband processing that is handled elsewhere. But it can be quite small, and we're seeing device prices that are quite low and phone prices in the $50 to $100 range at the low end. So those kind of things require quite a small processor, and that's why we have.
It really is cheaper.
Oh yeah. We have a whole product line devoted to that, and we're actually seeing enormous volumes in those types of phones in Asia and in emerging markets.
And so, for example, there's a Chromebook that came out last year, dual-core Cortex A15.
Yeah.
And it has 6-7 hours battery life. Let's say if it was big.LITTLE, it could have much better battery life.
Yeah, it depends on what you're running on it, but yes, it'll have a better battery life. And what we've been seeing on the workloads we've tested is about a 70% reduction in power for the CPU subsystem. And so that can improve battery life, but it really is workload dependent. If you're doing a lot of really intensive things and using the A15s all the time, you won't save as much. If you're running a benchmark, the purpose of a benchmark is to run the CPU as fast as it can go. big.LITTLE will save exactly 0 energy in a benchmark. But there are cases where you can maybe get a little bit extra performance running the extra cores. And in the way we really use our devices, it's not calculating pi to a million digits. We use our devices for things that ebb and flow in terms of the computational requirements. And for those types of things, big.LITTLE saves quite a lot.
What do you think about benchmarks? I mean, because lots of blogs just talk about the benchmark. As soon as there's a new phone, they just go and make the benchmark and show the score. But that's not real use case.
Right. I think benchmarks are quite limited in the scope. I mean, they're useful to understand how well a processor does at a certain task. But if you look at how the benchmarks are constructed, a lot of them are doing very complicated double precision math, floating point math, or running through JavaScript tests. And there are varying degrees of realism in the benchmarks themselves. And none of them today really reflect this burstiness that we see. This period of intense performance and these subsequent periods of lower performance. A couple that I will call out though, so Embassy's got one called Browser Bench that is a bit more interesting. It renders web pages and there's a pause between those page renders. So I think there's been an interest in the development of better benchmarks or better tests that represent how you and I use our phones. But today a lot of the things you see in the technical press reference Antutu scores or Linpack scores. Those are useful, but they're definitely not sufficient to understand how these devices will perform in your everyday life.
So is it possible for chip companies to fake benchmark results? Because that's what I imagine. Is it totally wrong of me to imagine that some company is like knowing, this is a benchmark, let's peak my voltage compared to a normal, or let's do some other kind of trick and show a better result somehow, even though it's not really true.
It's possible. I'm probably not the best one to speak about that. It's just not an area that I've spent a whole lot of time focusing on. I've seen some of the articles that I think you're referring to, but I think I'd probably refer you to the silicon manufacturers on that one.
So it might be possible to imagine some kind of way to test devices in real use case. Like I guess it would require a lab where you would have real people go and try to do real things in the phone and then measure how long it takes or something.
Yeah, I think there are ways to automate some of these things, and we're experimenting with some of that at ARM. But I do think we need, in this industry, a move towards more realistic benchmarks.
Because ARM has nothing to do with the x86 world. Everything is very optimized, right? And very multi-core. And
I think we're starting to see an interest in manufacturers of what have been x86-based devices converting to ARM low-power technology. So we're seeing an interest in using things like Windows 8.1 on ARM devices. And so I think there's a migration to ARM for some of these devices. Also with the x86 world, we're starting to see ARM-based low-power servers. It's not as much my area personally, but those ARM-based servers are able to bring a level of power efficiency to a domain where cost of ownership for a server and for a data center are really becoming dominated by power and cooling costs. So the fact that ARM can reduce those costs, I think, is very important, and it's causing this migration of a lot of those applications to ARM, initially in just certain cases, but I think that's growing over time.
So I really like to see more, I guess there is already, but productivity devices like laptops, desktops. But there is the Chromebook, but can you confirm we'll see much more?
Yeah, I think there's a lot of innovation in that area. So the Chromebook is one example. We're seeing a lot more development in the area of tablets that are convertible or have varying form factors. So we're very active with a lot of the OEMs, and there's a lot of activity. I have nothing to announce right now about that, but I think stay tuned. There's a lot of innovative new devices coming.
I guess 64-bit is going to enable lots of fast
64-bit can help.
ARM laptops.
Sure, yeah. Although 64-bit is not strictly required to enable that, 64-bit is really about improving the address range. It takes you beyond 32-bit virtual address range, which really takes you beyond that 4 gigabyte boundary on devices. So it can be useful for applications that are manipulating a lot of data at once. Video editing, augmented reality, things like that. We'll want to manipulate large amounts of data all at the same time using the virtual address space. So 64-bit helps with that, but it's not required. I think we're seeing very good devices based on ARM v7 technology, which is 32-bit fundamentally, but it has extended physical addressing, so you can go beyond the memory reach of 32 gigabytes in those systems still, even without going to the ARM v8 architecture. But that's coming, and I think 64-bit is going to enable newer high-end applications over time.
But when there's a new Cortex A57, A53, it's not only about being 64-bit. There's lots of other stuff that makes them faster or better?
Right. It's not just the architecture that changed with the A57 and the A53. Both of them have a brand new microarchitecture where we're doing a lot more with each, issuing a lot more instructions through the pipeline, for example. We're increasing our throughput. The memory systems are beefed up. The load store bandwidth in particular on A57 is up quite a bit. So the microarchitecture has been improved to the tune of 20 to 40% added performance on each of those. And that doesn't even factor in some of the memory improvements and the prefetching and all that goes on. So even running 32-bit code, both of those cores are going to be a big leap up.
Nice. So I can look forward to much more fun and cool and awesome ARM devices, right?
Yeah, absolutely.